Hello, this is a flipped classroom for general chemistry. First of all, this is the first lecture about the chemical bonding by VBT, valence bond theory. So I just want to summarize the background for the chemical bonding, and then in the two lecture, we'll continue with some kind of class activities and practice problem. So first of all, we have to know what is the chemical bonding. So actually, the chemical bonding is a force that link atoms together in a molecule. And normally, this kind of force is an electromagnetic force, one of the four fundamental forces in the universe. So as you may see in the picture, that we have two atoms that link together, the green atoms and the purple atom. So basically, each atom normally contains electrons, and as you know, electron has potential energy. So the energy of the electron can be maybe divided into magnetic forces and electronic forces. So in order to stabilize the energy of atom, all the electron in all the orbitals have to be fulfilled in order to reduce down the magnetic potential energy, thing like that. So the summation of the spin of electron has to be lowest. That means there have to be no unpaired electron left in the system. This is why your atoms link together. And the chemical bonding may be divided into four main types: the covalent bond, ionic bond, and metallic bond. And all the chemical bonding is based upon the the classification of chemical bonding is based upon their electronegativity. So first of all, we have to understand the electronegativity, this term. So if you look at my first example, that you can see one of the white atom linked together. So actually the electron is pairing, so they have some magnetic forces that link them together because of the opposite spin. So in order to destroy this kind of chemical bonding, we need some energy, and this kind of energy is called bond energy. So in the first type, two white atoms linked together, we have bond energy equal to A, kcal per mole, for example. And then next one, the black one, we have bond energy as well, which is equal to B, or B kcal per mole. So if I have white atoms that link together with black atom, the question is, what is the bond energy of this system? So the very simple answer for this question is the bond energy is equal to, yeah, of course, C. No. Actually, if you think about it, two white atoms linked together with bond energy equal to A, two black atoms linked together with bond energy equal to B. So actually one white and one black, the bond energy should be equal to A plus B divided by 2, right? So as the average, thing like that. But as I said, that white and black here, bond energy have to be equal to C, and actually it is equal to C, which is not equal to A plus B divided by 2. It's normally higher than, not normally, but always higher than the average bond energy of the white and the black. So what does that mean? From this kind of data, the guy called Pauling just say that if we think about the energy that linked two atoms together, it is not only because of the magnetic field of the electron, but actually, if you look back to this picture, actually the nucleus, which is positively charged, is trying to it has some electrostatic force, right? So the electrostatic force of the positive charge here withdraw electron, the bonding electron into the nucleus. So both atoms can do this, but these atoms may have different electrostatic force from the nucleus. So this is called electronegativity. So if, for example, in this picture, if the green one has higher electronegativity, so the pairing electron or bonding electron is closer to the green one, and this leads to the negatively charged of the green particle and positively charged of the purple particle. So for example, if the white has higher En than the black, then the white here contains positive charge and the black here contains negative charge. So the chemical bonding is not coming from only the magnetic field between two electrons here, but it also from the electrostatic forces between two atoms as well. So this makes your black and white has higher bond energy than the average bond energy of two white and two black. So this can be calculated as the delta En between white and black. So this is what you have learned from your high school chemistry. So to summarize, I want to give you some examples of the chemical bonding. First of all, two chlorine atoms linked together, we have covalent bond. Because both chlorine atoms are exactly the same, so the En or electronegativity is equal, and the delta En is equal to 0. That means both atoms has capability to withdraw electron into the nucleus equally, so there is no charge. So this covalent bond can be called as non-polar bond. But if you change from one of chlorine atom to hydrogen atom, for example, so H and Cl has different En, and from your high school chemistry you may know that Cl has higher En than hydrogen atom, and the delta En of this case is equal to 0.96. So Cl has stronger capability to take the bonding electron to the right hand side, and this causes your chlorine as partially negative and hydrogen atoms partially positive. So this is still called covalent bonding, and this is called polar bond. Unlike your sodium chloride, as you know that the sodium is a metal, right? So metallic atom has very low En, so the delta En between Cl and Na is 2.23, which is very, very high, and make your Cl as negatively charged and your Na is positively charged, and we call this as ionic bond. So what difference between among these three samples, chlorine, H, and Cl, and Na and Cl? So they are all, if you look at the delta En, right? So Cl delta En is equal to 0, and the delta En increasing up from Cl to HCl and to NaCl. So why we call sodium chloride as ionic bond? So ionic bond means the bonds of ion. So we have to prove that our molecules contains some ion or charge. So to prove this is very easy, right? Because if you have ion, if you have charged, then you have electricity. Your compound can conduct the electricity. But because sodium chloride is normally in solid phase, so that means your positive charge and negative charge stay still at the place, so they didn't move any bit. That means there is no conductivity in solid state. So you have to melt your sodium chloride down. So if you melt it down, sodium ion and chloride ion can move. Then if it moves, if they move, then we can see the conductivity, and this proved that your sodium chloride is ionic compound. Unlike HCl, normally HCl is a gas molecule. So in gas phase, that means your molecules is moving, right? In gas phase, it cannot conduct the electricity. So there is no proof that you have ion in the molecules. Even though if you dissolve HCl into water, this HCl can dissociate it very well into water because it is a strong acid and it conducts electricity as well. But the conducting of the electricity here is because HCl is dissociated to be H plus and Cl minus. But this is not dissociated by themselves. It's dissociated by the interaction with water. Unlike sodium chloride, it can dissociate it in liquid phase, and that indicate the charge in the molecule. Okay, last type is sodium and sodium, which has very, very low En, and we call this kind of thing as metallic bond. This is because both sodium atom has a very, very low En, so the electron in the molecules can move freely. So if we have a bulk metal, sodium metal, it conducts electricity very, very good. This is because each sodium atom has very low En, so electron can move freely, and if the electron can move freely, then it conducts the electricity even though in the solid phase. So to prove that your compound is covalent, metallic, or ionic, we have to prove it by the conductivity, or your En may suggest that if you have two atoms linked together by very high En for both atoms, then they have covalent bond. But if you have very low En linked together, low En atoms linked together, then it is a metallic bond. And if we have one of the atom is very low En, one of the atom is very high En, then we have charge separation. The low En contains positive, the high En contains negative. And if the charge separation is high enough, then you have the ionic bond. But if the charge is not very high, like HCl, it's just partially positive, partially negative, and it cannot conduct electricity when it moves, then we cannot prove that we have ion in the molecule, and we can still call it as covalent bond. But maybe we call it as the polar bond instead. Okay, this is the introduction of the chemical bonding. Now, we're going to look at the covalent bond, okay? Because we are going to talk about the valence bond theory, and then we will compare it with the hybridization theory and the molecular orbital theory afterward. So first of all, look at the covalent bond of the compound. Normally, covalent bond can described by octet rule. So oct mean 8. Octet rule is the rules of 8, for example. So what is the number 8 come from? So 8 can become from 1 plus 7, right? 2 plus 6, or 3 plus 5, 4 plus 4, or even 1.5 plus 6.5, for example. So what is the number of the octet rule actually means? So if you look into the atoms and look into the number of electrons, we have some kind of summation of the numerical things leads to the number 8, and it is because you have to fulfill it. As I said, the stable atom or stable particle, you have to reduce the potential energy of the particle things. So at least you have to lower down the electron spin to be 0, because unpaired electron contains a magnetic field. So in order to reduce out the energy here, so you have to pair them together, and to pair them together you have to fulfill your subshell, right? So to fulfill all the subshells at least, for example, if you have hydrogen atom or helium atoms, and you know that hydrogen atom is not stable, helium atom is stable because helium contains one s orbital, and the one s orbital of helium is fulfilled, so there is no magnetic pole. But the hydrogen atoms, one s contain one electron only, right? So we have magnetic field. Then if you have two hydrogen atoms that come close together, then a magnetic field of both electron gonna pair them up, okay, and make chemical bonding. So octet rule means you have to fulfill all the electron in both s and p orbitals. So OS and OP is orbital fulfilled, then you have the summation of the electron equal to 8. So this comes to octet rule. For example, if you look at your neon atom, you have 8 electrons already, so no bonding needs, right? But for fluorine atom, you have 7 electrons in the valence shell, 2 in S and 5 in P. So in order to fulfill all this thing, you need 1 extra electron. That means your fluorine has to use 1 electron of itself paired with extra electron from outside world, and then we have 1 chemical bonding, 1 covalent bonding, for example. And for oxygen atom, you have 6 electrons at the valence shell, so at least you need 2 more electrons. In order to withdraw 2 electrons from outside, you need a magnetic field, right? So you have to have 2 unpaired electrons, and this first unpaired electron gonna link with the opposite spin of extra electron outside, and the second electron here needs another 1 pair electron, right? To pairing with the extra electron with the opposite field, for example. Then for nitrogen, at the same time, so you need 3 bonds, and carbon atom need 4 bonds. This is what you have learned in your high school chemistry. So normally fluorine, as you can see, they can link together, make a single bond. Oxygen gas link together, make a double bond, and nitrogen gas link together as triple bond. Now comes to the questions that why there's no CC quadruple bond. So 4 electrons of each carbon link together, right? So we have in total 4 chemical bonding between 2 atoms of carbon, and we call this as quadruple bond. But why we have no quadruple bond in carbon element? So as you see that the world is driven by energy, right? We have to decrease down the energy in order to stabilize our system. So your carbon atom, if you want to reduce the magnetic field and make this kind of bond, because your carbon atom is very, very small, so in a very small area here, you have 8 electrons that condensed in between, right? So you increasing up the electrostatic charge, the electrostatic or electrical potential energy, if you want to say. So this leads to very high energy, very high electrostatic force here, and it is not stable, right? Because stable means lower energy, right? So in this case, carbon, instead of making 4 bonds together in just 1 pair, it separated, make it, link them together like a network covalent that we're going to talk about it later. But anyway, quadruple bond or quintuplet bond or sextuplet bonds, things like that, can be found in bigger atom, in bigger system, like the bottom row of element like ruthenium, tungsten, things like that. In a very, very big atom, they can make quadruple bond or even higher order of chemical bonding in between. Now, over octet, okay, if we look at the system, SF2. They are all octets, right? Sulfur is in the same group of oxygen, 16, right? Fluorine in group 17. So they link together like this. And if you have extra fluorine molecules, this fluorine molecule is octet as well. So, but anyway, you can create this SF4. And if you look at the sulfur atom in the center here, the valence electron of the sulfur is equal to 6 of itself, and then it links with 4 more electrons from 4 fluorine atoms. So at the end, you have 10 electrons in total, and make your sulfur over octet. But this can be found. What is the driving force for this phenomenon? This is because, as you know, every atom is trying to reduce down the chemical, the potential energy, thing like that. So sulfur has to take 2 more electrons from outside. Fluorine has to take 1 more electron from outside. So instead of taking electron from other fluorine, which is very high En, right? If the fluorine here encounter with the molecules here, which is sulfur, right? Sulfur-containing molecules. Sulfur has very low En comparing with the fluorine atoms. So fluorine atoms can then withdraw electron from sulfur easier than withdraw electron from the fluorine. Okay, then this is driving force. Fluorine, instead of take electron from another fluorine, it take electron from the sulfur, which is easier. So then we can synthesize this as a 4 as a product. Okay, but if we change a bit from fluorine to hydrogen atom here, okay, H to S, okay, combined with hydrogen gas. So what is the product? The answer is there's no reaction. There's no reaction. This is because your hydrogen atom has lower En than sulfur. So it cannot take electron from sulfur here. So it stay like H2 is good enough, right? It's good enough. Because it cannot take electron from sulfur, it cannot force the sulfur to be over octet. And the sulfur here is already stable. So it is not necessary to take more electron from hydrogen. So this system cannot be this reaction cannot be occurred. And then OF2 and F2. In this case, fluorine has higher En than oxygen atom. So instead of pulling electron from fluorine, from another fluorine, it can take electron from oxygen atom here, which is easier. But still, the reaction cannot occur. So why? So there's actually 2 criteria for the over-octet system. First of all, in this H2S case, as you can see that at least the En of the ligand or the terminal atom has to be higher than the En of the central atom. Okay, because the ligand can then take electron from the central atom and force the central atom to be over octet. Okay. But another criteria in the system of OF2 is more important. This is due to something. We go back to the octet. As I said, that the octet is coming from 2 and 6. Okay, 2 plus 6. 2 from the electron number of electron in s orbital when fulfilled. 6 is the number of electron in p orbital when it is fulfilled. So as you see here for SF4, right, the valence electron of the sulfur is more than octet. That means you need some other orbitals in order to bear other 2 electron, okay, extra electron. And because sulfur is in 3rd period, so your sulfur is not only has S and P, but sulfur contain d orbitals, right? So you can have electron put into d orbitals if you want something more than octet. But oxygen is in 2nd shell, 2nd period. K, L, M, N, O, P, Q. You remember this, right? K, maximum number of electron is only 2, and H for L, M for 14, right? So in this case, your oxygen is in second shell. You have only 2s and 2p. There's 2d. There's no 2d, right? That means you can put electron maximum just 8 into your oxygen atoms. So your oxygen atoms cannot be overoctet. So to be overoctet, the central atom, okay, the central atom have to be in the third period or beyond, okay. So you need the orbitals in order to overoctet, become overoctet. Now, what is the stable form of thionyl chloride, SOCl2? And explain your answer. Actually, for SOCl2, you can draw for different style. First of all, in the structure A, all atoms are fulfilled with octets. Cl, 1 bond. O and S in group 16, 2 bonds, right? Now, for SOCl2 in the structure B, right, sulfur is in the middle, and all atoms linked with the sulfur and make your sulfur overoctet as 10 electron, 2, 4, 6, 8, and 10 here. Structure C, oxygen in the center, and the number of oxygen of the electron in this oxygen here 2, 4, 6, 8, and 10. So oxygen here is overoctet. And for D, chlorine is in the middle, and then 2, 4, 6, 8, 10, 12. So your chlorine is overoctet. So what is the most stable form of SOCl2? So the worst answer is C, because as you can see from our criteria, that the central atom have to be in third shell, right? Oxygen is in second shell, so you have only 2s and 2p. So maximum of the electron that oxygen can bear is only 8. It cannot be overoctet. But S and Cl can be overoctet, and for the structure A, all are octet. So we have to go back and think about why your atoms have to have chemical bonding. This is because you want to stabilize the energy of the system, right? To stabilize the energy of the system, all atoms in the molecules have to take electron from others. So to take electron from others, actually, well, you need the En, right? You need the En. So En is the thing that describes how your atoms take electron from others. So S, O, and Cl, okay, all gonna take electron from others. So normally the higher En take electron better, right? So the lowest En will be in the center, because Cl has very high En, O has very high En. Then instead of sharing electron among themselves, they take electron from sulfur. Is easier, right? So this drives your system to be in the structures B, okay? Because chlorine take electron from sulfur is easier than take electron from oxygen, and again, oxygen take electron from sulfur is easier than take electron from chlorine. So all higher electron gonna take electron from the lowest En. So normally the lowest En atom will be your central atom in the system. Now we're going to look at the third type of covalent bonding, coordinate covalent bond. So look at this structure. We have here carbon monoxide. So actually normally your carbon contains 4 electrons and your oxygen contains 6 electrons. So when you think about a molecule like this, so first of all, what you have to do is you have to think about the very high En first, because your high En atom can take electron as many as it wants, right? So your oxygen atom here needs 2 more electrons to fulfill the octet. So it takes electron from carbon like this, and your oxygen is now stable. But the thing is, your carbon is not stable because the number of valence electron here of the carbon, free carbon, is 4, right? It share 2 more electron from oxygen and make your total number of oxygen of electron is equal to only 6. So it is less than octet, and it is obviously not stable. So to make it more stable, your carbon gonna take 2 electrons from anywhere in order to fulfill the octet rule. So it takes electron here from the oxygen. So instead of you have let I draw like this. So instead of you have a structure like this, the 2 electrons of the oxygen here gonna move here to here, right? So it is like your oxygen donate the electron, okay, to carbon and make the whole system as octet. So now your structure is similar to nitrogen atom with 5 electrons from each atom and make triple bond. So now your carbon monoxide has triple bond in the middle, but this triple bond constructed from 2 electrons from carbon and 4 electrons from oxygen. So if you want to count the valence electron, okay, as you can see here, the carbon has 5 valence electron around itself, 5 electron, right? And oxygen is 5 electron as well. But normally you have only you have 4 electron for carbon, so you have 1 extra electron. So your carbon contains negative charge, and your oxygen contains positive charge because you lost 1 electron to the carbon side. So whenever you make equivalent coordinate covalent, you have 4 more charge present in the molecules. Okay, and this is coming from your high school chemistry again. So coordinate covalent is something like this. Now come to AlCl3. Draw the stable octet structure of AlCl3. First of all, what I want to say is AlCl3 is not ionic bonding, because if we gonna melt, AlCl3 can be sold as white solid. Okay, I bought it actually. So AlCl3 white solid, when we melt it down, we can see that there is no electrical conductivity, anything. So this indicates that your AlCl3 is not ionic, and it is the covalent. So draw the structure of AlCl3. So to draw the structure of AlCl3, Al will be the central atom because it has very low En, and then you surround it with Cl. Cl take 1 electron from Al for sure, because Cl has higher En, right? And Cl needs only 1 electron because it is in 17, group 17. So 1 electron, 1 electron, and 1 electron, you make 3 bonds. Now your Al has only 3 valence electron. So in total, it shares electron with chlorine, right? So 3 from itself and 3 more from chlorine, which is equal to totally 6 electrons, and it is under octet. So you have to make your aluminium to be octet. So the actual structure of it will be like this. Okay. So Al, because of the under octet, not stable, so Al take 2 electrons from any Cl atom nearby and make your coordinate or dative bond from Cl to Al. Cl is electron donor and Al is electron acceptor, and this make your Cl positively charged and your Al is negatively charged. Okay, this is the coordinate covalent. We're gonna play something with your AlCl3 in the class. Okay, we have various structure of AlCl3 which is very fancy, and we're gonna see it later on in the class. Now, resonance. This is the 4th type of chemical bonding, of the covalent bonding. Resonance. If you look at the AlCl3 again, it is not necessary for Al to take electron from the top Cl. It can take electron from left Cl or right Cl as well. And if you take electron from the top Cl, you have the first structure. If you take electron from the left Cl, you have the second structure. And if you take electron from the right Cl side, okay, you have the third structure. Actually, all these three structures, the electron of the three structure are different, right? The way you draw it, and you can change the structure 1 to structure 2 to structure 3, and then change it back to structure 1 as well. You just move electron around. For example, to change the structure 1 to structure 2, you move the electron from the left Cl coordinate to fulfill the octet for Al. Then the 2 electrons from the top Cl is not necessary for Al anymore, so it turned back to the covalent up there, and you have the second structure. And to make the third structure, you just coordinate the electron from the right hand Cl, and then return your left hand Cl electron, the dative one on the left hand, back to the covalent at your left hand side, and you then create the third structure. And again, you can move it back to the first structure. So actually, electron moves around. Okay. So because the electron moves around, that means you have less electrostatic force. Is electron, right? Electrostatic, you mean you put the electron stay still at somewhere, right? But now electrons move around. We call this as delocalization of electron, or resonance. Okay, so resonance is actually, we call it technical term, delocalization of electron. Okay. So your electron is not localized or stay at some place, but it moves around. So electron contains negative charge. So if your if your negative charge runs around, that means you reduce the electron density, reduce the charge density, and then your potential energy dropped. Okay, so because the potential energy depends on the charge density, sorry, depends on the charge density or depends on the electron density. Okay, so if you can release or decrease down the electron density or decrease down the charge density, then your potential energy is decreasing, and everything is more stable. So as you can see that if you look at the formal charge here as well, right, for the first structure, your formal charge is on the top, positive charge, and the second structure is on the left, and third structure is on the right. Okay, so you lower down the charge density because you are now average the structure for. So actually the structure of AlCl3 is somewhere in between. Okay, you may draw it like this: Al, Cl, 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 right? So each Cl, you have 2 electrons that stay still. So 2 electrons from top and left and right is moving, so we can draw it as the dashed line like this. So the charge of the Al is -1 or 1 minus, but the charge of each Cl is 1/3 plus. Okay, 1/3 plus. Like this. As you can see, after resonation, after delocalization of the electron, charge of Cl is decreasing. Okay, and this indicates the lower potential energy, and your system is stabilized. Now under octet, this is the last example, the last type. This is rare type. Okay, as you can see that if you have lower octet system, then you have coordinate covalent to stabilize it. Okay, but now under octet is something more difficult. Okay, NO2, because the total number of valence electron from nitrogen is 5, from oxygen is 6, okay, plus 6. So totally 17 electrons, which is the odd number. But octet rule is 8, which is even number. But the total number of electron is odd number, so you cannot make everything, or you cannot fulfill everything with 8, which is even number. So at least one of atom here, N and O, has to be something not equal to 8, okay, but maybe it's very close to 8. But because N and O are in second shell, so you cannot surpass the number 8. So at best you have to put 7 electron in some atoms here and make it under octet, because 7 is less than 8, right? So normally if you draw thing, okay, let I put it here, N has lower En, it have to be in the middle. O is higher En, so you surround it, okay, you surround the nitrogen with O. And because O has higher En, we're gonna consider the oxygen first. Then each oxygen has to take 2 electrons from the nitrogen in order to fulfill the needs of electron of the oxygen atoms. Then your nitrogen normally has 5 electrons, right? Now you draw only 4. That means you have 1 more electron left in nitrogen atom. And for this structure, the total number of electrons of the nitrogen is 5 plus 4, which is equal to 9, and over octet. But the nitrogen cannot be over octet, so you have to move something around. So it is similar to how you move electron in carbon monoxide and how you move electron in AlCl3. So now, because your nitrogen has extra electron beyond 8, so what we can do is move these 2 electron to the right hand side, for example, and then we have this kind of thing. Or you can also move to the left hand oxygen as well, and you have exactly the same, but you just flip the molecules into a 180 degree like this, okay. So if you move 2 electron, bonding electron here to oxygen atom, because oxygen has higher En, right, so it can take 2 electron here, and then you have this structure. And if you look at this structure, oxygen on the right hand is 6 electron bonding with other 2 electron from nitrogen atoms, it is octet, okay. Oxygen here on the left hand, you have 1, 2, 3, 4, 5, 6, and 7 electron sharing with another 1 electron from nitrogen atom, and your oxygen is octet, okay. But now because you have 7 electron around oxygen atoms, not only 6, okay, that means your oxygen is now negatively charged. For nitrogen atom 1, 2, 3, 4, you have only 4 electrons at the center, okay, around the nitrogen itself. So valence electron of nitrogen is equal to 4. It is positively charged because normally your nitrogen contains 5 electrons, right? But because of this 4 electron, you bound with others 3 electrons from oxygen atom, from ligating oxygen atoms. Then your total number of electrons is equal to 4 plus 3, which is 7. This is the best that we can do, okay, because the number of electrons is odd number, not even number. So we have to make it very closer to 8, and this is the best number that we can do, okay. So these are the summarize of your covalent bonding. Now in the class on Tuesday and Friday, we're gonna have some more examples of the molecules, okay, for valence bond theory that is more complicated. So you may just go back and read your high school chemistry again, and then try to draw things, molecules that you may know, and then I will give you more example. Some molecules in the class will be neutral, some molecules Some molecules is positively charged, some molecules is negatively charged, thing like that. Okay, so let's have some fun in our class, and then this is all for the first flipped classroom for the course. Thank you very much, and see you in the class. Bye.